In the context of electrical service design, particularly for multi-unit dwellings like apartment buildings, understanding three-phase load calculations is crucial. This is especially important when dealing with a mix of single-phase and three-phase loads. Let's delve into the specifics of why certain calculations are performed, particularly concerning range loads and the conversion of single-phase air conditioning loads to their three-phase equivalents. Firstly, let's address the range load calculation. The reason the range load is divided by 2, specifically in a scenario where you have 20 ranges each rated at 12 kilowatts or 12,000 volt amps, is because in many three-phase systems, these ranges are supplied by 2 phases. This configuration aims to distribute the load more evenly across the 3 phases, promoting system stability. By dividing the load by 2, we are essentially focusing on the load contributed by each of those 2 phases. This step is critical for accurate phase load balancing. Now, let's move on to the conversion of single-phase loads, such as your 53,000 volt amps air conditioning load, into an equivalent 3-phase load. While it might seem counterintuitive, especially when thinking of volt amps as a direct measure of load, the conversion is necessary due to the potential for imbalanced loads to create voltage imbalances in a 3-phase system. These imbalances can negatively impact equipment performance and overall system efficiency. The core concept here is that a balanced 3-phase system is ideal, where each phase carries an equal share of the load. When single-phase loads are introduced, they inherently create an imbalance. To compensate for this, we use a correction factor to estimate the equivalent 3-phase load that would produce a similar effect on the system. The correction factor commonly used is the square root of 3, approximately 1.732. This factor accounts for the phase shift inherent in a 3-phase system and helps to approximate the equivalent balanced load. In your specific scenario, with 53,000 volt amps of single-phase air conditioning load, the calculation to convert it to equivalent 3-phase load is as follows. Equivalent 3-phase load equals single-phase load multiplied by the correction factor. So 53,000 volt amps multiplied by 1.732 equals 91,796 volt amps. This result signifies that the single-phase air conditioning load of 53,000 volt amps has a similar impact in the 3-phase system as a balanced 3-phase load of 91,796 volt amps. This conversion is not about changing the actual power consumption of the air conditioners, but rather about accurately representing their effect on the 3-phase electrical system. This equivalent 3-phase value is what you would use in your overall load calculations to determine the required service size. To summarize, the process involves firstly calculating the demand load for the ranges, taking into account the diversity factor allowed by the National Electrical Code (NEC). Secondly, converting the single-phase air conditioning load to an equivalent 3-phase load using the factor of 1.732. And thirdly, adding these 2 values along with any other 3-phase loads to determine the total equivalent 3-phase load for the building. This total is then used to size the service entrance conductors, overcurrent protection, and other components of the electrical system. Remember, the goal is to ensure a safe, stable, and efficient electrical system for the apartment building. This involves understanding not just the total load, but also how that load is distributed across the phases, and accounting for any imbalances that may arise from single-phase loads. Failing to properly account for these factors can lead to voltage imbalances, overheating, and potential equipment failure. Let's consider an additional example to further illustrate this concept. Suppose you have a workshop with a variety of single-phase power tools. The total load from these tools is estimated at 25,000 volt amps. To determine the equivalent 3-phase load, you would multiply 25,000 volt amps by 1.732, resulting in approximately 43,300 volt amps. This value would then be added to any existing 3-phase loads in the workshop to determine the total load on the system. It's also important to note that the NEC provides specific guidelines and tables for calculating demand factors for various types of loads. These demand factors allow you to account for the fact that not all loads will be operating at their maximum capacity simultaneously. For example, Table 220.19 in the NEC provides demand factors for household ranges and cooking appliances. These factors can significantly reduce the calculated load for these appliances, especially in multi-unit dwellings. Therefore, always consult the latest edition of the NEC and any applicable local codes when performing electrical load calculations. Furthermore, remember to consider any future expansion or changes in load when sizing the electrical service. It's always a good practice to provide some extra capacity to accommodate future needs. In conclusion, calculating three-phase load requirements for apartment buildings and other similar applications requires a thorough understanding of load balancing, single-phase to three-phase conversions, and the applicable codes and standards. By following these guidelines and consulting with a qualified electrical engineer or contractor, you can ensure a safe, reliable, and efficient electrical system. Always remember to prioritize safety and adhere to all applicable codes and regulations when working with electrical systems. Now let's delve a little deeper into why the square root of 3, or 1.732, is used as the correction factor when converting single-phase loads to equivalent three-phase loads. This factor originates from the geometric relationships within a balanced three-phase system. In a balanced three-phase system, there are three voltages that are equal in magnitude but are displaced by 120 degrees from each other. These voltages can be represented as vectors, and the relationship between them forms an equilateral triangle. The line-to-line voltage in a three-phase system is equal to the square root of 3 times the phase voltage. This relationship is fundamental to understanding why the square root of 3 is used as a conversion factor. When a single-phase load is connected to a three-phase system, it draws current from only 2 of the 3 phases. This creates an imbalance in the system, as one phase is not loaded at all, and the other 2 phases are loaded unevenly. To determine the equivalent three-phase load, we need to find the amount of balanced three-phase load that would produce the same voltage drop in current flow as the single-phase load. This is where the square root of 3 comes into play. By multiplying the single-phase load by the square root of 3, we are essentially calculating the equivalent three-phase load that would have the same impact on the system's voltage and current. This conversion is not exact, as it assumes a purely resistive load and does not account for any harmonics or other nonlinear effects. However, it provides a reasonable approximation for most practical applications. It's also important to note that the square root of 3 is only applicable to balanced three-phase systems. In imbalanced systems, the conversion factor may be different, and more complex calculations may be required. In addition to the square root of 3, there are other factors that can affect the accuracy of load calculations. These factors include the power factor of the loads, the voltage regulation of the system, and the presence of any harmonic currents. Power factor is a measure of how effectively electrical power is being used. A power factor of 1 indicates that all of the electrical power is being used to perform work, while a power factor less than 1 indicates that some of the power is being wasted. Loads with low power factors, such as motors and inductive loads, can draw significantly more current than loads with high power factors. This increased current can lead to voltage drops and overheating. Voltage regulation is a measure of how stable the voltage is in a system. A system with good voltage regulation will maintain a relatively constant voltage even when the load changes. Poor voltage regulation can lead to voltage drops and equipment malfunction. Harmonic currents are currents that are at frequencies that are multiples of the fundamental frequency, typically 60 Hz. These currents can be generated by nonlinear loads such as electronic devices and variable frequency drives. Harmonic currents can cause a variety of problems, including overheating, voltage distortion, and equipment damage. When performing load calculations, it's important to consider all of these factors to ensure that the electrical system is properly sized and protected. In many cases, it may be necessary to consult with a qualified electrical engineer to perform a detailed load analysis. The NEC provides guidance on how to account for these factors in load calculations. For example, Section 220.18 allows for a demand factor to be applied to motor loads, taking into account the fact that not all motors will be operating at their full load simultaneously. Section 220.61 provides guidance on how to calculate the neutral load in a three-phase system, taking into account the presence of harmonic currents. In addition to the NEC, there are other standards and guidelines that may be applicable depending on the specific application. These standards may include those published by the Institute of Electrical and Electronics Engineers, i.e., the American National Standards Institute (ANSI), and the National Fire Protection Association (NFPA). It's also important to consider any local codes and regulations that may be in effect. These codes may have additional requirements or restrictions that must be followed. When designing an electrical system, it's always best to err on the side of caution and provide some extra capacity to accommodate future growth and changes in load. This extra capacity can help to prevent overloads and ensure that the system is able to meet the demands of the building or facility. In addition to proper load calculations, it's also important to ensure that the electrical system is properly installed and maintained. This includes using qualified electricians, following all applicable codes and standards, and performing regular inspections and maintenance. A properly installed and maintained electrical system will provide years of reliable service and help to prevent accidents and injuries. In summary, performing accurate three-phase load calculations is essential for designing a safe, reliable, and efficient electrical system. This requires a thorough understanding of load balancing, single-phase to three-phase conversions, and the applicable codes and standards. By following these guidelines and consulting with qualified professionals, you can ensure that the electrical system meets the needs of the building or facility and provides years of trouble-free operation.